Hello and welcome to the fourth of the lectures in this week 6 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. So far this week, we have looked at two of the important components in a fuzzy inference system, that of the fuzzy if-then rules, the rule base itself. We have looked at a general schematic diagram of a fuzzy inference mechanism, and we moved on to the second of the important components of an FIM, that of the inference engine itself. In here, we have looked at fuzzy relational inference. Of course, we have seen it only for a single rule, and that too for a single input, single output rule. In this lecture, we will look at how to infer when we are given a multi-dimensional input rule. That means multi-input, single output rule. A quick recap of the mechanism of fuzzy relational inference. So we are given a single input, single output rule. Firstly, we would like to get a relational representation of this rule. That means we would like to relate the antecedent A, which is a fuzzy set on X, to the consequent B, which is a fuzzy set on Y, and capture it as a fuzzy relation on the Cartesian product X cross Y. Note that X and Y are the underlying input and output domains. So essentially, we want to build a fuzzy relation from the given rule. Once we have built this, given an input A dash, which is again a fuzzy set on X, we obtain the output B dash, which is a fuzzy set on Y, by composing A dash with this relation which captures the rule. We have seen that this composition operator is essentially a function which takes a fuzzy set on X and a fuzzy relation on X cross Y and outputs a fuzzy set on Y. We have seen that so far, from what we have seen, a fuzzy inference mechanism can be looked at as a quadruple, wherein X and Y are the input and output domains. R of AABJ, it represents the rule base, and the final operation, the symbol Maltese, it shows that there is some inference being applied. It consists of all the operations that are required for the inference itself. Specifically in the case of fuzzy relational inference, it turns out like this. So we have the input-output domains and the rule base, and the inference is captured by these two things. One, the relation which is obtained out of the rule base, the rule so far that we have seen, and the composition itself. Often it is convenient to write it in this short form. Well, let's look at an illustration. We are given this rule, temperature is low, then the fan speed is slow, and given the input temperature is average, we would like a reasonable inference, something like fan speed is medium. So when you translate it into notational symbols, then we see that we have a rule of the form A implies B, and given an A dash, we want a B dash. We know that this can be obtained by composing A dash with the relation R. And what is R? It is that fuzzy relation which captures the rule. In the previous lecture, we have seen a few illustrative examples. Let's revisit a couple of them with a specific purpose in mind. Note that we have a rule, a single input, single output rule, and in this case, we would like to use the implication operator to capture the rule into a relation. A is given as this, and B is given as this. That means on X and Y, we have 3 points for discretization on X, and Y 2 points for discretization in the domain of Y. We are using the Gödel implication, and we have seen that this is the relation that we will extract out of this rule. Now, given the input A dash as follows, as 0.40 and 0.6, we apply the SUP-T composition, because we are in the regime of CRI, composition rule of inference. SUP-T composition with the minimum T0, and we saw that we obtained the output to be 0.4, 0.6. So this is the output fuzzy set. Now firstly, if you look at it, there is an FRI, specifically it's a CRI. That means the composition is a SUP-T composition. In this case, we are using a SUP-min composition. But note that R is obtained by using the implication as the function f. This is a shorter way of indicating it. Now, in yet another example, we used T0 to generate the relation. Once again, A and B remain the same. To generate the relation, we have used minimum T0 and taking A and B, in some sense doing some operation that is kind of an outer product, but using the minimum T0, we have come up with this relation. We have seen this in a little detail in the last lecture. Now, the relation itself was obtained using the T0, but the composition is the in-phi composition because we are in the regime of BKS inference, Bangalore cohort subproduct inference. And for the implication here, we have used the clean beans implication, which has given us max of 1 minus x, y. And we have seen that when we give this input A dash to this relation, this is the output that we obtain. So when you take this row into this column using the clean beans implication, these are the values you get, and then it's actually infimum over this, so minimum of them will be 0.4, minimum here is 0.6, and that's how we get 0.4, 0.6. This is an example that we have discussed in the last lecture. And if you were to write this inference, you see that x, y, and the rule base are fixed, and we know the inference is captured by the relation and the composition. In the B case, it is an in-phi composition. That is clear. In this case, we have used the clean beans implication. Note that the relation itself has been obtained by T0. Well, what is interesting is this. We are given AB and an A dash, and now when we used BKS with the clean beans and obtained the relation from T0, especially the min, we saw that this was the output we got. And when you use CRI with SUP-min composition and obtain the relation from the rule using the Gödel implication, we saw that this is essentially the same output that we have got. So it appears that for this A dash, from two different inferences, we are actually obtaining the same output. Let's take the same inputs and try to change some operations. The same rule, we will use an implication to capture the relation. We have used the Gödel implication itself. So this is the relation that you would get to capture this rule when A and B are given us this. Now let's use the B case inference. Earlier, when we captured the rule using an implication, we used the CRA inference in SUP-TM, SUP-min composition. In this case, we are capturing the relation also with an implication, and we are applying the B case, which essentially uses an implication. So to capture the rule, we have used Gödel implication, and in the inference, we are using the clean beans implication. Let's look at what happens here. Now when you look at this, note that we have to take this row into this column using the clean beans operation. A quick check will show you that if we are using the clean beans implication, 0.41 will be 1, 0.4, because it's an implication, if x is 0 it is 1, if y is 1 it is 1, and 0.6.4 is 1 minus 0.6 from 0.4, max of these two, which is again 0.4. So that's how you get this. Now 0.41 means 1, 0.8 of the clean means applied to the clean beans would give you 1, 0.61 would also give you 1. Now minimum of all of this is 0.4, and minimum of these three ones is 1. So what we see is, while earlier the inference that we got from two different inference schemes with A dash were same, in this case with exactly the same rule and inputs, but with a slightly modified or different combination of operations for obtaining the rule, the relation from the rule and the composition, we see that they are no more true. This spawns many questions. A few of them definitely we will be addressing as we go forward. Well, this was just to illustrate that for a given A dash, the B dash is not unique. It depends on so many operators that you use. So the degree of freedom is quite a lot, and it depends on the choice of operators that you have to. Well, now let's go into looking at how fuzzy relational inference can be applied when we are given a MISO rule. What is a SISO rule? Input dimension is only one. What is a MISO rule? There are multiple input dimensions. So we say if x tilde, x1 tilde is a1 and x2 tilde is a2, so once if x1 tilde is am, then y tilde is b. What are these x1 tildes, x2 tilde? They are again linguistic variables which can assume fuzzy sets or linguistic values defined over the domains x1, x2, x3, so on to xn. So the dimensionality of this rule is n. We have seen an example of the rule. If temperature is low and humidity is high, then fan speed is fast. Low is the linguistic value a1, high is a2, and fast is b. Note that a1 is defined over x1, it's a fuzzy set from x1, a2 is fuzzy set from x2, and b is a fuzzy set from y. Now the question is, how do we capture this rule into a relation? Let's look at that. How do we represent a MISO rule by a relation? This calls for yet another operation which we call the antecedent combiner. What essentially we are doing is taking the partition product of a1 and a2. Much like how we took the partition product of a and b to obtain the rule, but here it's with a difference. So we are going to consider a1 and a2 as both of them as antecedents. So the semantics here could be quite different from relating an antecedent to a consequent. For the moment, let's stick with just these two dimensions, a1 and a2. So we can combine them, these antecedents, using a binary fuzzy logic connector, but a binary associative fuzzy logic connector. Why associative? Because we might have more than two antecedents here. So we have seen that we don't have an m-dimensional input, so we need to be able to combine m of them. So in that sense, the rule now becomes R of a1, a2, b. It is being captured as follows. First, we use an antecedent combiner to combine a1 and a2. Then we apply the operation f, which relates this combined antecedent to the consequent. Let's look at an example. So let's represent this multidimensional rule as a1, a2 going to b, and the input now will not be a single a dash, it will also be multidimensional. In the case that we are considering, it will be a1 dash, a2 dash. Let's give some values to these labels. Let a1 look like this. That means on the domain of x1, we are discretizing it at 4 points, and this is the fuzzy set a1. Similarly, a2 is discretized with 3 points on x2, and b, again, we are obtaining as a fuzzy set from y, which is discretized into 3 points. And for the antecedent combiner, let us use the operation min, just to keep the working example simple. And to relate the combined antecedent to the consequent, let us use the Lukasiewicz integration. Now, combining a1 and a2 means what? Essentially what we have done earlier to obtain the relation from the rule. You can think of it once more as an outer product. For instance, so our a1 was this, and b, a2 is 1.6.8, Now we want to talk about Tn of A1 from A2. It's nothing but A1 transpose and A2. What do you mean by this? 0.1, 0.7, 0.7, and apply the minimum operator 1, 0.6. So once again, we are actually taking 0.9 and multiplying with this row vector, but the multiplication operation is given by 1. So clearly, what you would get is 0.9 and 1, minimum of 9 is 0.9, 0.9 and 6 is 0.6, 0.8 and 1 is 0.8, 0.8 and 0.6 is 0.6, 0.7 and 1 is 0.7, 0.7, 0.6 is 0.6, so this is the matrix that you would get when you combine A1 and A2 using the minimum and minimum as the antecedent combination. And that's exactly what we have here. Now, this is combining the antecedent. We still need to use the consequent of the rule to build the relation. So that means this operation is pending, and note that this is the F operation and it is given by the Lukasiewicz implication. Now, how do we do this? Look at this. We want to now build a relation for this rule. Now, there are two antecedents and a consequent coming from x1 cross x2, x1 cross x2 cross y, 3 dimensions. And so the relation R is over these 3 dimensions. So if you look at them like this, R of xk, yj, zi, then you want to build this from the membership value of xk in A1 and membership value of yj in A2, and using the F operation, the membership value of zi in B. Now clearly, this R is a 3-dimensional relation. So now, it's difficult to represent it in 2 dimensions. So, a better way to look at it is by fixing one of the components. Let's fix Zi and let the other two vary. So, which means essentially, we are looking at the combined antecedent acting upon just one component of B. What do you mean by this? Look at this R of Z1. This is the matrix that we've got. And using the F operation, where Zi is actually 0.1. Note that earlier we would have had only one column if it was just one antecedent and one consequent. Now, because we have combined these two antecedents we have a matrix here. However, it is the same outer product that we are going to take. So how do we do this outer product? It's simple. This is the combined antecedent. We take the outer product with one of the components first and repeat the process over each of the components Z1, Z2, Z3. And to do this, we are using the operation F, which is the Lukasiewicz implication. Well, let's look at doing this. R of Z1 is a combined antecedent, and using the implication, Lukasiewicz implication, and this Z1, we need to obtain one part of the relation. Remember, this relation itself is a 3D relation. If you apply this, this is what we will get. Now, let's try to understand this from the calculation point of view. How did we get this component? We are taking the outer product. So, with 0.9 and 0.1, we need to apply the Lukasiewicz implication. When you apply this, x is 0.9 and y is 0.1. It is minimum of 1, 1 minus 0.9 plus 0.1, which is essentially 0.2. Now, if you take 0.8 here and 0.1 here, then by fixing x to be 0.8 and y to be 0.1, you will get a second component. So if you go through like this, essentially you are only doing some kind of an outer product operation and you will be able to fill this matrix. And this is R of Z1, then we need to do R of Z2, R of Z3 also with this scheme of A1, A2. Since Z1 and Z2 are same, if you look at it, Z1 and Z2 are same, what we would get is the same for R of Z1 and Z2, and R of Z3 is different. So now this is the three-dimensional relation that we have obtained. You could think of it as three 2D matrices, perhaps on 3 sheets of paper. Now, this is building the relation representing the root, a single multi-input, single output. Now, we need to be able to infer with this. Let's for the moment take a very simple case wherein the given inputs A1 dash and A2 dash are in fact singletons. That means what? They take the value 1 at only one of those 4 discretized points, the underlying discretized point, and 0 in everywhere else. Now, what we need to do is, remember, R is a 4 cross 3 cross 3 matrix. So, when you fix one of those components, Z1, you get a 4 cross 3 matrix. It's a 4 cross 3 matrix, but we have 3 such matrices. So, from dimensionality point of view also, given these two, we need to be able to obtain a 4 cross 3 matrix to be able to compose. Now, how do we do this? Once again, we use the antecedent component K, which is the minimum in this case. Now, it is easy to see that if you take the outer product of A1 dash and A2 dash with respect to minimum, this is the matrix that we get. Now, this is what we need to compose with R of Z1, R of Z2, and R of Z3, essentially with R. Now, since we are dealing with CRI, it makes our calculations much simpler. You could think of performing such an operation, taking this page on which this matrix is written and superimposing it on this matrix, on the page where this matrix is written, and component wise you take the min and take the max min. So if you do that, 0 on point 2 is 0, 0 on point 3 is 0, everything will be 0 except where this is 1, which is 0.5. And similarly, everywhere else here it will be 0 except at 0.6. Thus, when you compose this with the original relation R, this obtained combined input, this is what you would get as the output. Let us look at one other example only from the calculation point of view. Let us look at another example. For this example, let's take x to be just x1, x2, y again to be y1, y2. That means both these domains are discretized by just 2 points, and z by 3 points. Now since we are only trying to get the calculations right, let's start with the given inputs. A1 dash, let's assume it is 0.3, 0.5, and A2 dash, which is 0.4, 0.6. Now, when we want to do the inferencing, assuming we have the rule represented in terms of this relation, which in this case, as you can see, will be 3-dimensional matrix. So let's start with obtaining the combined input which has to be used for the inference. Now, we need to use the minimum operator here. Once again, this is essentially taking the outer product, it's 0.3, 0.5, min with 0.4, 0.6. So what we obtain is the minimum between 0.3 and 0.4 is 0.3, 0.3 and 0.6 is 0.3, 0.5 and 0.4 is 0.4, 0.6 and 0.5 is 0.4. So let's take this. And now what we want is, let's call this S. Let's replicate this here. Since R is a relation from x cross y cross z to 0, 1, we saw that we can fix up z1, z2, z3 and then vary the first two components, in which case we get a three-dimensional matrix, of course, but it's a 2 cross 2 cross 3. So we will get 3 2 cross 2 matrices. So allow me to write them directly. So this R of z1, R of z2 and R of z3. So let's arbitrarily fill values here. Assume that these are the ways in which we have actually obtained the relation, and the relation looks like this. Now what we are doing is, this is the combined input that we have. All we are going to do is, we are going to take component-wise minimum and finally the maximum. So we need to do between these two sigma. Let's look at it. So we start with 0.3, 0.3, 0.3 and 1. The minimum of that, we need to take the maximum of the minimum between the component-based elements. Minimum of 0.3, 1 is 0.3. Minimum of 0.3 and 0.8 is 0.8. Minimum of 0.4, 0.4 is 0.4. 0.5, 0.3 is 0.3. And the maximum of them is actually 0.8. Similarly, if we take these two matrices and once again use this sup-min composition, so we have 0.3 and 0.6. The minimum of that will be 0.3. 0.3 and 0.7, minimum once again is 0.3. 0.4, 0.5, which is 0.5. 0.5, 0.5 is 0.4. 0.5, 0.5 is 0.5. And we need to take a max of them, which is 0.5. Finally, we need to take sup-min composition between these two matrices. So if we take 0.3 here, so perhaps circular, 0.3 and 0.4 here, the minimum is 0.3, 0.3 and 0 is 0, 0.4 and 0.3 is 0.3, 0.5 and 0.2 is 0.2, and we need to take the maximum of them, and what we get is max of this is 0.2. So essentially, finally, the overall output B dash that we get is 0.4, 0.5 and 0.3, which is an element of F. Well, you would have noticed the cumbersome, tedious way to compute the output when we have a multiple input, single output rule, and this is just one multiple input, single output rule. So if you have many multiple rules, then it becomes computationally even more cumbersome. Is there a way to reduce the computational effort? Yes, we can propose many, but the question is, would it still give the same answer we would have obtained by following this procedure? Now, these are questions we will definitely take up as we go along, and answering these questions will once again show us the theoretical structures that we have discussed and developed, the crucial role they play in answering these questions. We know that as a general fuzzy inference mechanism can be represented by this quadruple. In the case of single input, single output rule, we saw that we could obtain a relation from just an operation F, which related the antecedent to the consequent, and we needed a composition operator. In the case of multi-input, single output rule, we not only need an F, but also an antecedent combiner K, and of course the composition operator. A quick recap. So we have been discussing fuzzy relational inference. In the previous lecture, we looked at fuzzy relational inference for a single SISO rule. In this lecture, we have looked at how to perform FRI in the presence of a single multiple input, single output rule. Of course, it is clear that the knowledge about any domain in which you are trying to capture and reason in cannot be captured in one single rule. We need multiple rules. We will look at fuzzy relational inference for multiple rules in the next lecture of this week. We will also see that it necessitates aggregation of pieces of information, either the representation of the rules themselves or the local outputs. So next lecture, we will deal with how to handle multiple rules when we are inferring with fuzzy relational inference. Once again, a good resource for the topics that we have covered today is the book of Drenkov, Hellandun, and Reinfrank. And also you will see the case of MISO rule being handled in this book on fuzzy interpretation. Glad you could join us for this lecture. Hope to see you soon in the next lecture. Thank you once again.